Hello again from the Phoenix Mars Mission Science Operations Center at the University of Arizona in Tucson, Arizona. I'm Sarah Hammond, Public Affairs Manager for the mission. Well, we're ending our third week on the surface of Mars, and it's been kind of a busy week around here this week. We've been doing a lot of looking, we've been digging and scooping, we've been dumping and shaking and sifting, we've started baking. We're going to start sniffing real soon and also doing some tasting. And to tell us more about these sensory experiences today are Peter Smith, the principal investigator of the mission from the University of Arizona, Tom Pike, science team member for the optical microscope from Imperial College London, Mark Lemon, stereo surface imager lead scientist from Texas A&M University, and Nilton Reno, science team member for Atmosphere from the University of Michigan. And Peter, why don't you lead off our discussion today?
Thank you, Sarah. Our last televised press conference was marking the end of our characterization period. That's the time we chose to test our instruments and to do our first touches of the soil and actually kind of get our calibrations all done so that we're ready for our science phase. Today is our first science phase press conference, and so we have a lot to report. The most wonderful news I can give you right away is that we have samples from the surface inside of two of our instruments, the microscope and the TIGA. And today we'll hear about the microscope examination, but the TIGA information will be coming shortly after. Not today, but next week. Just to recap, to get back to the big picture of this mission, our mission was inspired by the data returned from Odyssey spacecraft, and the Odyssey scientists, including our own William Boynton, told us that there was ice near the surface surrounding the polar caps. And so the Phoenix mission is specially designed to try and understand what is going on inside of this ice. This is important because on Earth, polar regions preserve traces of climate change and even signs of preserve signs of life and organic materials. So this is a really key place to look on Mars to see if the same thing is true there. On the Earth, we use very sophisticated instruments to do these experiments, and we brought similar sophisticated instruments with us to Mars to do this analysis. The orbiters have been very helpful in the process of getting us to Mars. We've had the Mars Global Surveyor and the Odyssey that have provided data sets that we use to choose our landing site. But it wasn't until we had the Mars Reconnaissance Orbiter with its high-resolution camera that we learned we had to avoid rocks. And we were very successful in avoiding rocks, as you can see in the pictures that Mark Lemon will show just after this. And this has been really useful for us because some of the regions in the polar, some of the areas in the polar region are extremely rocky. We also use our orbiters for communications, and really during our entry, descent, landing, we got signals back from both Mars Reconnaissance Orbiter and from Odyssey, and also from Mars Express. So the orbiters have been very useful in communicating our signals back to Earth, and in fact we're getting so much data back that we're getting about twice the data volume that we're told to expect, and this has caused some consternation among our team because you have to write sequences for all the data gathering that we do with our instruments, and these sequences take a fair amount of time. They have to be checked and rechecked, and so our team, who are working on the difficult Mars time schedule, which of course started at the worst possible time at night shift and has now progressed to graveyard shift, has left the team a little stressed and tired. So if you see some tired people around the building, you know that they're probably on Mars time. So for the first time since Viking, we have instruments that have samples from the Martian soil inside and are ready to start analysis. We are, excuse me, our results from these analyses are going to be used to inspire future missions that will come to Mars and hopefully take over where we leave off, because we're bound to raise lots of questions. Okay, the next thing I want to talk about is digging into the Martian soil, and this has been something we've been doing for the last week or so, and Digging in soil has been, of course, one of our key activities because we're trying to find an ice layer, which we're told exists. We see a hard surface underneath the lander, and now as we dig into the soil, we see a hard, bright surface right within just a few inches of the upper layer. And if I can show the first picture, that is our first dig test into the soil, and then next to it you can see flashing on and off is where we've done our sampling. So the first dig test actually disclosed a bright surface just a few inches down, 2.5 inches, and so we've taken our samples right next to that, and we've delivered those samples to our TIGA instrument and our microscopic instrument. But there's still some debate about that bright material, so in the next slide we can see what we've done very recently is to try and dig a little deeper in both of these areas, and we see the exposed ice. So this is, I'm sorry, this is the second slide, which shows the same two locations as it was sampled a few days ago. Now the latest picture will be the next one that just came down today, and that's not there it is. So that's the exposed ice, is just as we've seen it today as we dug a little deeper into these two trenches. And now, not everybody is sure that this is ice, so there's been some debate within our team, and the debate centers around perhaps there's a salt layer above the ice, which would be very bright and white also, so we don't want to discount that possibility, and some people hold on to this theory and some don't. So we've had a fairly intense debate among the team whether that's ice or salt, but everybody believes there's ice near the surface. Whether that's it or not is the question. The other question is this thick ice that goes down deep beneath the surface, or perhaps this is a thin layer and we'll be able to scrape through it. So scraping with our tungsten carbide scrapers on the scoop is really a high priority for us. The next topic is delivery to the TIGA instrument, and my next slide shows the first delivery to TIGA, which was a big scoop full of material dropped onto the cell, and it stuck and would not go through the screen, and you can see it's laying there on top of the open doors of the TIGA instrument. The TIGA oven showed no response. We tried using our little shaker device day after day for 4 days, and after 7 shakes, if I can show the next slide, yesterday we were successful, and this is a picture showing that the material has slid down over the screen, sort of like going over a cheese grater, and some of the material has gone inside and has filled the oven, and we sent the commands for the first operation last night, but we don't have our data back yet, so we can't report on any results today. This will be coming early next week. So this is a very exciting time for us. We find the soil is very clumpy, it's very sticky, it's an unusual soil, not at all like the types of soils we've used in our tests, which work just fine with all the instruments, and so we've developed another method of collecting samples, and that is to tilt the scoop a little bit and then vibrate it with a little power tool we have on the scoop. So it vibrates it a little and it shakes some soil down and it kind of rains down onto the screen or onto the delivery port. And we think this is the method we're going to be using from now on, and we'll hear more about that. So next week, pay attention, we'll have results from TIGA, and we'll be delivering samples to our wet chemistry cells, and to show off to introduce my next speaker, I have a wonderful animation done by our co-investigator Eric DeYoung, and this will introduce our next speaker, Tom Pike. So let's watch the animation. Here we are from our launch pad, looking up at the brightest object in the sky, which, as we zoom in a little bit, turns out to be Mars. And we're going at an incredible rate of speed towards Mars in this animation, a little faster than the spacecraft, which took 10 months. And we didn't slow down quite as rapidly, but in any case, we're zooming in on our spacecraft on the polygonal terrain, and there's our Mecha instrument. And now a wonderful picture taken with the microscope. Tom, will you tell us about it?
Thanks very much, Peter. Yeah, this is the highest resolution image of the soil of Mars, and we're looking at a sample that was delivered using, well, a variety of sequences we had to have operating to get this soil in. This is the first sample delivery to an instrument inside a spacecraft since the Viking missions over 30 years ago. And we didn't know so much about the soil when we came down. The remote sensing satellite data told us a lot about the ice. It didn't tell us too much about the cohesiveness of the soil, and we've had to work that out as we went along. So if we go to the next slide, just to show you what we needed to do to get this soil into the microscope station. As we zoom in here, we see the microscope station, which shares its box with the wet chemistry laboratory. Those are the 4 cells on the right-hand side. And at the front, you will see a little U shape. And if we see right in front of me, we have a mock-up of the very same box. And right in a chute here, we have the substrates poking out. Now, these are what we use to capture the sample that we deliver to the field of view of the optical microscope. So during the delivery phase, the substrates are sitting outside of the box, and they're ready for the robot arm to deliver a sample. So if we go to the next image here, the next animation, we see that the way that we had the robot arm deliver the sample in this particular case was not just a dump of the soil as had been done with TIGA, but a sprinkle. And we tested this. We took 3 days in testing how to go about this sprinkle so that we would just get, we were hoping, the right amount of material on. We wanted enough material for it to be representative of the soil that we're looking at, but not so much that we would completely cover the substrates and not be able to see the individual particle sizes. So the robot arm came over the top of the microscope box, and a vibrator that is inside the scoop, which is used for when we are actually digging into hard material to loosen that. We've been improvising with that to try and see that we get a good sample to us. So if we go to the next slide, this is what actually happened. And you can see the scoop there poised just above the chute. In fact, it has just delivered the sample. You can see on the top of the box the particles, somewhat clumpy, and then just below the broad white area in the middle of the chute, those are our substrates outside, and this confirmed that we got a good sample of Mars material. So that's how we get it onto the substrates outside of the box. We now need to be able to bring that in front of the field of view of the microscope. And the next animation shows how we go about this. So we see the sample wheel in yellow sticking out of the box, and what we have to do, we have to rotate that round so that it comes round in front of the 2 microscopes that we have. Today I'll be presenting data from the optical microscope. That's the orange microscope on the right-hand side. So the wheel has come round, and then we can move the wheel into the focus position. Just in front of that orange optical microscope, we have the atomic force microscope that we hope to be bringing into operation in the next week or so. Okay, so on the next image, we can see what we have captured. So just to give what we're seeing right at the bottom of that image are the shadows from the atomic force microscope cantilevers. So they're all ready for operation. We've multiply imaged those. And if we zoom into the particles that we've collected here, this is a particle about 50 microns across, about the diameter of a human hair, a little less than the diameter of a human hair. And we see that in this case, we have both a greenish part of the particle to the top. The supposition at the moment that that could be olivine. We know we see olivine elsewhere on Mars, but at the moment we can only go by the color. Below that we see the very characteristic orange coloration that we see in the Mars soil. And if we move the camera just a little bit, the optical microscope just a little bit focused out from the substrate holding this material, we can see that that clump is not, that particle is a clump of even finer particles. And we see that in the background. Particles right down to the resolution of the optical microscope. So we're going down to the individual pixels, which are 4 microns across. Okay, there's some other particles of interest as well. If we look at the, if we zoom in to a particle which is in the bottom right-hand corner here, and this is a glassy particle. If we look at this more closely, you see it's more rounded, and this may very well be a volcanic glass. And it is quite possible, if we look at the full image again of our substrate, that what we are looking at here is a potted history of Martian soil. We have the hard particles, these black glassy particles that over millions, even billions of years have slowly been weathering down, becoming iron enriched, that gives the orange material its characteristic color. And we're seeing that process captured on the variety of particles that we're looking at the moment. Now, this isn't the first set of particles that we've been able to image. We already had our substrates out to just passively collect material that was kicked up while the Phoenix lander actually came down with its retro rockets, somewhat blasting the material into the air. And we were ready to capture that. And if we look at the next slide, we see a comparison on the left-hand side of what we caught during landing, on the right-hand side of what we've got from the scoop. And the scale bar at the bottom is 1 millimeter across. What we see in the dust fall is a whole variety of very fine particles, right down to this 4 micron resolution on the left-hand side. On the right-hand side, we have what the soil has looked like once we brought it in. We can see that we've indeed got just what we were looking for, which is this field of particles well separated so that we can say something about their shape. But very importantly, we see that the clumping that was very evident when we were digging at the level of the scoop in the few top centimeters of the soil is even repeated down to the tens of microns that we're seeing here. These are tiny clumps, maybe made out of thousands of particles apiece now. But there's cohesive forces. This is obviously a very sticky material right down to the finest scale. Okay. And finally, if we look at the next, we've got a whole variety of substrates that we look at. We look at 6 substrates at a time. And this particular substrate we fabricated at Imperial College in London out of silicon. And it is a series of holes and pegs of different spacing. And the idea of this substrate is that we are able to tightly grasp the particles for future analysis with the atomic force microscope. Again, you can see the shadow of the atomic force microscope beams at the bottom of that image. And so what we have on the third strip from the left is that we've been able to capture a very good variety of particles. These are pegs which are 5 micron spacing, just about the size of the larger Mars particles that we'd be looking for. And of course, we're very eager now to zoom in probably another factor of 40 times. So we can extend that animation a little further, Peter, in a week or so, and see not just what the particles look like as maybe a little fuzzy blob, but we'll be able to, we hope, look down at the detailed substructure of those particles and actually see below the resolution of our optical microscope. Okay. We now have Mark Lemon, who is going to be talking about what the stereoscopic imager has been producing from its look around the lander.
Thank you. The Surface Stereo Imager has been very busy every sol, helping to contribute to making Phoenix a success. The camera is a tool both for helping to guide operations. It provides sort of our hand-eye coordination. It helps us pick where to use the arm, what to do, how to sample. And it's the way that we survey the site and connect what we see to other things that we know. Peter and Tom showed examples of some of the images that SSI has taken in the course of guiding the operations. I'd like to show one more example. This animation came down today, earlier in the day, Sol 18, and it shows the robotic arm poised over the trench at the commencement of digging operations, and as this animation plays, it will... I'm sorry, I'm waiting for the animation to actually play. The animation, the dig occurred in 3 parts over the day. The Sol 18 was our first serious dig, actually using the RA digging commands as opposed to the sample acquisition commands. And those commands were issued 3 times in the course of the dig over a 2-hour period. During each of those 3 digs, the SSI took 7 images spaced out over the dig. So I think we'll just be able to show you later what is happening in the trench during that time. We use that to monitor how the trench evolves over the course of the dig. What stuff do we uncover and then bury? How does the ice change its appearance once the digging is over? I'm sorry, I shouldn't say ice, the bright material. And I think what we see in the animation is very intriguing, and in particular at the end here we see a fairly stable look to it. There are very, very subtle changes related to the changing illumination, but no other strong variation. And you can see that the RA is just whizzing by in some of these frames, so you see it blurred a little bit. So this is a very dramatic way, I think, to visualize what's going on Mars, what went on Mars just a few hours ago. So SSI, in addition to its operational role, is our tool for surveying the landscape. It's the camera that can sit back, look at everything in color. It has human-like depth perception. So we have been taking advantage of that and acquiring our high-resolution color pan. And I'd like to show you the scene that we saw on Sol 16. This is looking at the landscape toward the west. We use images like this to understand the landscape as a whole. We can zoom out to the horizon and see distant features that are observable from orbit. You can see the hills fading into the dust in the background, as well as a small number of large rocks. That is exactly what we expected to find in the area that we were targeting for the landing. You can see some of the polygons in the distance as we pan closer to the camera, but then this also connects us to the stuff that we're actually sampling. So you see here in the scoop, the sample that on Sol 16 when this picture was taken was just about to go into the microscope. So the dirt that you're seeing there is the dirt that Tom just showed in the microscope. And that's the robotic arm camera poised looking into the scoop there, and the very slightly dusty solar arrays at the bottom of the screen. So a successful mission really requires understanding the context for all of the observations that we take. We are acquiring samples, putting them into the instruments, and coming up with a detailed understanding of a very small part of Mars. With the images, like the next one is another example, we can connect these small-scale observations to a larger scale. So this is showing a view to the southeast, and we can zoom in and see the kind of detailed features in our landing site. The rocks here have a very blocky texture. Just as a reminder, Phoenix landed in an area that was affected by the impact that created Heimdall crater, and you're seeing relatively smaller rocks, rocks up to ballpark of a foot across. We're not seeing the large boulders that we saw at other places that caused us not to land there. The rock in the right-hand side there, Toto, is very interesting to me with its flat top, sort of an icebergy appearance, although it is a rock. And then as we pan out, we get to connect to the site as a whole. This is where we start seeing some of the troughs. We see the rocks just perched on top of the surface there. And going further and further out, we're still seeing mostly smaller rocks mixed in with the polygons. Until we get to the greatest distances where we can see the horizon. We start seeing 2 larger boulders there. Essentially, we expected to see boulders of the meter-plus scale, about 1 per baseball field in terms of size. And then at the far upper right-hand side, you see a bright glint. That is actually the back shell. You see the gold foil on the inside of the back shell that helped us land here. One interesting thing about that is if you look at the back shell closely, there is no parachute visible. While the parachute is clearly visible from orbit, the parachute must be lying in one of the troughs and hidden from our view. It'll be interesting to see if the wind blows it around any, if it ever shows up from our point of view. The next panorama I want to show is part of a complete set that we're trying to take. Ultimately, we will have a 360-degree view of our site in full color and using our binocular vision, using both eyes of SSI. This one is particularly important because this section, which was taken in the evening of Sol 14, actually comes up near our workspace. So you're looking essentially 10 feet away from the lander right now, just beyond Humpty Dumpty National Park. And as we pan across, we'll actually be coming up onto the area just behind Humpty Dumpty itself. Right now, we actually started just past where the trench is. And then as we go down, or as we continue to go across, we'll get into an area which connects up with Sleepy Hollow. So we're connecting the polygons and the troughs that we're seeing in the broader site with the ones in our immediate workspace. So I want you to imagine now standing, crouching in this area that we're looking at. One of the things that we can do with SSI is not only take color images, we can take stereo images. We take advantage of the camera's binocular vision, and we can use our depth perception to model the landscape. So the next graphic shows the landscape modeled. Right now it's only in black and white, but it shows this small section of Mars, and we're actually crouching down where we were just looking before in the color panorama, and kind of turning our head around. You can see some of the polygons and troughs, the little hilly texture that you see. These are only about 8 inches tall, but if you sort of imagine yourself crouched down, they start to look a little more dramatic and impressive. I think this view is excellent. This is the sort of thing that we're trying to build up for the whole site. By the next week or two, we should have completed our mission success panorama, the panorama that we want to take to show from the spacecraft out to the horizon in full color and stereo, so that we can show an image like this, only in color, and fly around the entire landing site. So that's something that we're about halfway done with right now. We started on Sol 13, and through about Sol 18, we're about halfway done. So now, the last thing I want to mention that SSI does, we've been spending a lot of time looking up at the sky. SSI helps with the weather monitoring. There's a lot of dust on Mars, and we're measuring the amount of dust in the sky, and we're measuring the winds and seeing how the winds are blowing the dust around. And to talk more about the weather and how we're looking at it, here is Nilton.
Thank you, Mark. Phoenix is also studying then the weather and the climate in the polar region of Mars. And in order to do this, Phoenix has a meteorology station and a LiDAR that were built by the Canadian Space Agency. It has a mass spectrometer that's being used to measure the composition of the atmosphere. And it has 2 cameras that are going to be looking at the atmosphere and around near the surface. And it has a few other instruments, including the microscope that Tom Pike talked about. With the microscope, we'll look at the dust particles, including the particles that are raining out from the atmosphere. And can I have the first slide? So in the first slide, we have, for example, the weather report from yesterday. The temperature at the landing site has been between minus 30 degrees Celsius and minus 85 degrees Celsius. So it's really cold compared to the Earth, even the Earth polar regions. The pressure is very small. Like yesterday was 8.35 millibars. On Earth is 1,000 millibars. So it's a very small fraction of what we have on Earth. And the wind in the landing site has been pretty calm. Like yesterday was 14 kilometers per hour or 8.7 miles per hour. And we haven't been seeing too much in the action in terms of dust storms. But there is lots of dust in the atmosphere. And in fact, the atmosphere of Mars at the landing site has been like a really polluted place on Earth with lots of fine in the air. So decreasing the amount of solar radiation reaching the surface by about 10%. Can I have the next slide? So in the next slide, we show a little dust storm downwind of the landing site. Okay, this one shows 3 big dust storms over more or less the place where we landed. And those are very common both at the beginning of the spring and at the end, towards the end of the fall. So we expect to see some of those at the landing site, hopefully at the end of the mission. some of us will be very excited about making measurements in those conditions. And the amount of dust will be so much that the surface can get really dark. Less than 10% of solar radiation might reach the surface. So, and I have one more slide. Okay, this one is showing a regional dust storm. We have been seeing lots of those, and it's close to a really deep valley in the ice there that's 3 kilometers deep. So it's the cold air rushing down this canyon and lifting dust downwind of it. And that dust is swirling around and moving around the planet. And where we landed is quite safe because it's upwind of this region. So all this dust is moving away from the polar cap and away from the lander. And as you can see, really around the polar cap is very wind. The dark areas that we see there are sand dunes. So there's lots of sand dunes around the polar cap. So I have one final slide too. Okay, this one was made by Mark Lemon with the camera. And it shows on the left is just the background sky that you can see sort of dust when we look vertically with the camera. And the one on the right is a stretch version, and also its difference between sequence of images, and show us the dust moving with the wind. So we haven't been seeing any big dust storm, but we have seen lots of dust moving with the wind. So it's regions of more or less dust content moving, like what you would see outside in Tucson at this time of the year. Now to finish talking about the weather, what's really important is that in atmospheric science we cannot do controlled lab experiment to test theories and our understanding of our own atmosphere. But we can go to other planets like Mars and make measurements there and test the theories that we have that are sort of tuned with our bias towards what we understand of the Earth's atmosphere. So it's really important to go to other planets, especially Mars that has a much simpler atmosphere without too much clouds and without ocean. And another really good thing about Mars is that there's lots of dust in the atmosphere there. And we don't understand how dust gets from the air into the atmosphere and how it interacts with climate. In fact, this is responsible for one of the largest uncertainty in global climate prediction today. So we are going to learn a lot with this mission. I'm really excited to be part of it.
Okay, thank you, Nilton and panel. We're going to go to questions. We're going to start here in the theater. Please wait for the microphone and say your name and your organization. Back here, Alan.
I'm Alan Fisher with the Tucson Citizen. This question is for Dr. Pike. You mentioned when you were looking at some of the close shots from the MECA optical microscope, particularly the black glassy material, that you felt that showed that material had been weathered. Are you able to determine if that weathering is from wind or from past interaction with water?
Well, the black glassy material will slowly wear away from the outside, its outside surface, and that can be for a number of causes. It can be just from being jostled around within the wind. It can be because there is water on the surface. Now, when I say water on the surface, that doesn't necessarily mean it has to be at the bottom of an ocean or on a beach. This can be just the merest surface monolayer of water that might come from the ice underneath, and that will slowly work away. We're looking at dust that has been around for up to 4 billion years, and so even the slowest process can wear it right down to this very fine reddish material that we end up with. So it's very difficult to say definitively with the resolution that we have as to what that process is. We hope when we go in with the atomic force microscope that we will get better clues, because we'll be able to look at the individual particles and at the surfaces, and that may give us a better indication of what at the moment is a pretty open question.
Just to be clear, at this point with the optical microscope, we're not able to make that determination of whether it was wind or whether it was water that caused the weathering.
Up to this point, we haven't been able to make a definitive confirmation that water has been involved.
Thank you, Tom. Is there another question here in the audience? Right here? Go ahead.
My name's Deanna Morgan with Fox 11 News. I was wondering, what will it take to find out what that bright surface is, whether it's salt or whether it's ice?
we need to gather a sample of it and put it in our instruments. They're specifically designed for telling us what the material is. The TIGA instrument is very sensitive to even slight amounts of water, and if it's a high concentration of water, then they'll tell us exactly what the fraction of water to soil is, and the MECA instrument will tell us if it's salt. So we have just the right instruments on the surface here to answer those questions.
Thank you, Peter. Go ahead.
I also wanted to know, it was mentioned that there would be, and maybe it was meant to be a joke, but tasting. Will that actually happen?
Well, you could think of the wet chemistry cell as kind of a laboratory tongue, if you like. It's it can taste salt, it can taste acidity, and while it doesn't look like a tongue, it kind of acts like one, and will send us the signals back so that we can make a material just like that, and we can literally taste it.
Thanks, Peter. Another question here? Or let's go to the phone then. Is there a question on the phone?
Yes, my name is Jim King from Times, West Virginia.
Go ahead.
Okay. Would the most common soil, for example, at the Spirit site, be a close approximation to the soil we're seeing at Phoenix due to global wind transport?
Yes, I think that what we're seeing more and more confirmation of is that the soil and the dust that is settling out are really one and the same material when you get down to the individual particle sizes. What we are seeing at this particular site, though, is how the particles have adhered together, how they've clumped up. And that does appear to be more site dependent. So, yes, we're seeing that we probably have at the particle scale a sampling of the whole of Mars in just one microscope slide. The weightings may be a little different depending on what site we're at, but we're seeing indications. For instance, the olivine may not have come from nearby. It may have come from thousands of miles away and have been lofted and brought to mixed up with the more generalized reddish material that we're seeing everywhere.
Thank you. Is there another question online?
Am I online?
Go ahead. Speak
Yeah,
up.
this is Dave Perlman at the Chronicle.
Go ahead, Dave.
The question, there's a difficulty here simply between watching it on the screen and listening. But anyway, I'm trying to find out what the significance of those volcanic particles are, the black particles. Maybe somebody could talk a little bit about what kind of evidence that provides as to past environments because of the degradation of the volcanic stuff.
Yeah, the glassy particles are probably what the soil would start from. If we could turn the clock back to when we first had erosion of the volcanic eruptive material, the magma that comes out onto the surface, it would break down into these glassy particles. It would be produced actually directly from the eruption. And we see from far away, from remote sensing, there is a lot of evidence of glassy particles everywhere. But this is the first time that we've actually been able to image them this close up as individual particles. So that is the starting point. We know that Mars has then had these billions of years to weather the material down. And at the same time, new material is being revealed. So you see a continuous process captured at any one point from relatively unweathered material, this glassy material, to this much more weathered, degraded, chemically altered material, which is iron enriched and which forms the majority of the particles that we're looking at.
Thanks, Tom. We have another caller on the phone line. Go ahead, please.
Hi, this is Ann Ryman with the Arizona Republic in Phoenix. I had a question about, you mentioned this is the first time in more than 30 years that you have Martian soil inside scientific instruments. Could you just clarify the difference between what this lander can do and what the rovers did?
Sure. The rovers were specifically designed to study rocks. And in looking at rocks, they could understand the ancient environment in which those rocks formed. And so the rovers were given mobility in order to get to the rocks and remote sensing equipment in order to find the rocks. So their role was to find interesting rocks, go over to them, kind of grind off the outer surface layers. It could be a weathering rind, and then put instruments against the rock and measure their composition and take a microscopic image of them and do some remote sensing with infrared spectrometry. So those are the kind of things they're able to do. The difference with Phoenix is we're able to actually get soil and ices off the surface, and this is a more active, younger surface, and put them into very sophisticated instruments that can modify those materials in a way that we can understand the minerals, the chemicals, and the microscopic shapes and sizes of these particles. So there's quite a bit of difference here. I think the MER rovers are looking at ancient Mars inside of rocks, and we're looking at modern Mars in the soil and the ices.
Thanks, Peter. Another caller on the phone lines. Go ahead.
Hi, this is Ken Kramer for Spaceflight. Can you hear me?
Yes,
Sure.
yes.
Yeah, hi. I'm just wondering, you mentioned that these are volcanic, and I guess I thought you were going to be surprised if you saw volcanic material there. So are you surprised, and what is that telling you?
Well, we've seen, well, rather from remote sensing, we have seen that there is this glassy material quite commonly seen around Mars. So we're not surprised. I mean, one of the things that we can do with a microscope, as you can see, we're spreading out particles over a large field. So one individual particle may be 1 in 1,000 of what we're looking at. So we're able to look down at rather very small percentages of what might be making up the overall soil. So just being able to spread out the particles means that we're able to differentiate a lot of the processes and a lot of the stages of the particles that are taking place. So we're not surprised to see volcanic material. We know that essentially that's where it all came from originally, and we've seen this from remote sensing. What is new is seeing it at this resolution and seeing the individual particles.
Thanks, Tom. I believe we have one more caller with a question. Go ahead, please.
Oh, hello. This is the Times West Virginian. Regarding Tega, is it possible that the screen is filtering out material with the cohesive properties, thus biasing the sample?
Well, it's hard to tell. You don't actually see the material that goes into the Tega oven. The particles have to be smaller than the screen sizes, but if you looked at the microscopic images and saw the 1 millimeter scale bar, that is the size of the openings in the Tega screen. So you can see the particles are all much smaller, much smaller than that screen. And it's the clumping and stickiness of these tiny particles that prevented it from going through. So I suspect, as you might imagine, as the dam broke and the particles all of a sudden careened through the screen, that you would get a mix of all the different types. But I can't positively say that, but that's my suspicion.
Thanks, Peter. Is there another question here in the theater? Alan, go ahead.
I want to direct this to Peter, please. In terms of the dig, that's the ongoing extension or deepening of the trenches, where does that stand in terms of reaching to the hard, solid feature that we were hoping to? Is that an ongoing effort, and will we be seeing that soon?
Well, if you look at the trench picture that I showed, and the one that Mark was showing, his little animation, you could see what looks like choppiness. It's like you're using the blade of the scoop to drag across the ground, and if it's a very hard material, it'll chatter, and you can kind of see some chatter marks there. So this is hard material, there's no doubt about it. We would like to really test the hardness by using our scraper on it next, so that'll be happening over the next few days. I don't know exactly which day we'll do it, but sometime in the next week. And that gives us more purchase on the ground, and we can really apply more force and a stronger material to it. So if it's a thin layer, we should be able to crack it open. If it's a very thick layer, we might be able to scrape down just a few millimeters.
Go ahead.
You know, everything that you all are presenting is very exciting and new. I'm just wondering if there's anything in particular, whether it be from the weather or the images or the soil, that stood out in your minds as being maybe exceptionally intriguing at all?
Well, I think I would say what's really impressed me about the landing site is looking around the site as a whole with the color images. It's all Martian yellowish red. It's the same color that we expect from the other sites. When you zoom in, everything is just different brightnesses, but the same basic color. And in this, utterly Martian landscape, when we dig just a couple inches down, all of a sudden we see something that stands out more than anything we've seen from a Mars lander before, in terms of the imaging and the color difference. So that impresses me with how much it just shows off how unique and interesting this stuff is.
All right, go ahead. Sorry,
A
Milton.
comment from the weather. What was impressive is how well mixed the atmosphere is. Like the dust is very well mixed within the first few kilometers of the atmosphere, and how much the temperature has been changing, and the amount of dust sort of constant since the beginning of the mission. Okay.
Peter or Tom, do you want to add to the discussion?
Well, I think that partly it's just zooming in at this length scale that we haven't seen before, seeing the particles, the individual particles that we knew were there. We knew that they had to be very fine in the scattering experiments that we'd seen. But this is the first time that we've been able to see them against a background, do particle size distributions, and start to put data in at the bottom of the length scale for another planet. The first time that we've reached down to this level.
The thing that impressed me was looking down at the lander leg and seeing what looked like exposed ice, something called Snow Queen, and then looking under the lander to the Holy Cow feature. This was truly a surprise to me, and one thing I love is that we get a close-up picture of that first exposed ice. I think it's called Snow Queen, is it? Snow Queen, and it has all kinds of modulations in it. There's little pits, there's a little what looks like a crack, there's level changes. It's not just a flat sheet of ice at all, it's got structure. What's causing that structure? So I think before we end this mission, we're going to pretty much lay waste to our national park system that we've developed, and we're going to expose this ice table as much as we're able with the arm, and we're going to look at the shapes underneath the soil that can't be seen from orbit or even from Mark's camera without using the arm. And this will be new territory for to explore, and something wonderful is likely to come out of it. So stay tuned, and we'll see what's under the surface. We'll peel back the surface layers.
Thank you, panel, for today. Thanks for the questions. Before we sign off from Tucson, I want to wish all the gentlemen a happy Father's Day this weekend. We'll talk to you again next week, and until then, please continue to check the several websites for updates on the Phoenix Mars mission. Talk to you soon. Thanks.